Welcome everyone to the session 3 of World of Groupcraft 4 conference. The first speaker of this session will be Pravin Kumar from IISER Mohali, and he will be speaking on Brunnian planar braid groups and Brunnian doodles. Over to you, Pravin. You may start.
Yeah. Thank you, Soumyadev. I thank all the organizers for giving me this opportunity. So I will begin my talk. The title of my talk is Brownian planar braid groups and Brownian doodles. So this is a joint work with Dr. Vallari G. Bhardago and my supervisor, Dr. Mahendra Singh. So finding a homotopy group of a sphere is one of the most interesting problem in topology. So this following exact sequence connects the Brownian braid to the homotopy group of sphere. So we have following exact sequence where S2 is just a Brownian braid on a braid on sphere, and where the Brownian D2 is just Brownian braid on the disk, which is called classical Brownian braid. So a braid is said to be Brownian if it becomes trivial after removing any of its strands. So this exact sequence shows the importance to understand this kind of group in this braid-like groups. So for example, a Brownian braid on a surface braid groups are well studied. So in this direction, we decided to explore the Brownian subgroups on planar braid group, which is also called twin groups. So what is twin group? So we will consider the two parallel line y equal to 0 and y equal to 1 on the plane R2 with n mark points on each line. We will consider the collection of all configuration of n arc in these infinite strips, connecting the n mark point on the line y equal to 1 and those on the line y equal to 0. We impose two conditions that each arc is monotonically downwards and no 3 points have point in common. For example, in figure 1, it's a twin on 3 arc. All the arcs are monotonically downward. There is no triple intersection point. Whereas figure 2 has one triple intersection point. So this is a non-example of twin. So two such a twin are said to be equivalent if one can be deformed into the other by a homotopy of arc fixing the endpoints such that through the homotopy, this condition 1 and 2 holds. Each arcs are monotonic and no 3 points have points in common. The equivalence class, we will call it twin or also called planar braids. Placing one twin on the top of the other gives you another twin. This defines a group operation on the set of our twins on a fixed number of arcs. And we denote this group as Tn. It's called twin groups or also called planar braid groups. So consider this elementary twin shown in the figure 3, which has only one double point. So we denote this twin as Tn. And it's easy to see that any twin diagram can be written as a product of these Ti's. That is, we can keep one Ti's on the top of other. And it's also easy to see that keeping Ti on the top of another Ti it can be homotopic to a configuration without any intersection point. So Cohen proved that this group Tn, which forms a right angle Coxeter group, has a following presentation. It's generated by this Ti. Each of them are involution, and with the following two defining relations. One says that this is involution relation, and second says that it's far commutativity. That means if the index are far apart, they commute. Then we say a twin Brownian if it becomes trivial after removing any of its strands. This set of all twin on n strand forms a normal subgroup in Tn. For example, if we consider a 3-strand twin, the figure shows the twin shown in this figure is an example of a Brownian twin. So if I remove any strand, for example, if I remove this third strand, what picture I will get is with this picture, which is in the middle. Then now I can apply my homotopy to make it a trivial strand with no crossings. And it turns out that this Brownian T3 is just a group isomorphic to Z generated by this element, which we read as T1, T2 whole cube. Now it's interesting to ask what is the structure of this group. So when n equal to 4, this group turns out to be a free group of infinite rank with the basis of this form, where this x1, x2, x3 are element of the specific form. The key idea of this proof is that we have a nice normal form for the coset representative of this group, and we use the Rademacher-Strayers method to obtain this free basis for this group. So when n is greater than or equal to 4, the Rademacher finding such a normal form for coset representative is not feasible. So we couldn't able to apply the Rademacher-Strayers method there, but we somehow managed to argue that it at least forms a free group. So that this subgroup, Brownian twin group, is a free group for all n greater than or equal to 3. So the one reason to study these twin groups are its connection to this low dimensional object called doodles on two sphere, which also called planar knot theory. In 1979, Fenn and Taylor defines a doodle as an embedding of finitely many circles on two sphere without triple intersection. Later, Cohen extends this idea to consider as an immersion of circle on a fixed closed oriented surface. So by doodle, we mean a generic immersion of finitely many circle on a closed oriented surface such that no triple or higher intersection points are allowed. For example, these are the two doodles which are drawn on this plane, though it is on two sphere, which has no triple intersection, and it's an immersion of three circles. So we define an equivalence relation on a set of all doodles, stating that the two doodles are equivalent if one can obtain from the other by the finite sequence of following two moves, which are called Rademacher moves. First one is add in or delete in of monogons. Second move is this add in or delete in of bigons. For example, this first figure, using this two move, we can see that this is equivalent to a trivial doodle on three component. So that I can apply my R2 move on this region, which remove this particular bigon. So I applied my R2 move. Then I just applied some homotopy, which I just slide each of the circle to become a trivial doodles on three components. And here the main reason to study twin groups or doodles, it's a connection between them. So if you have any twin, then we can do this closure operation. That is, we will just close this each strand, the first mark point on the top to the first mark point on the bottom by a strand. So by doing this for all strands, we get the immersion of circle on two sphere, which is a doodle on two sphere. So starting with any twin, by doing this closure operation, we will get doodles. So Cohen proved the converse, that if every oriented doodle on two sphere is actually a closure of some twin. So it's sort of subjectivity of this map. So this is the relationship between this planar braid and this doodles. Having this theorem in mind, we can define this following terminology. The twin index for a doodle on two sphere is just a minimum n, such that there is a twin on n strand whose closure is equivalent to D. So then, like a Brownian link, we can define a concept called Brownian doodle. A Brownian doodle is just a non-trivial doodle, which becomes trivial if any of its component is removed. For example, if we consider this figure, if I remove any circle, any component, I will get the trivial doodle. For example, in the second figure, if I remove this red color circle, I get this blue color and purple color circle with the bigon which created. Now I can remove this bigon to become a trivial doodle on two components. Similarly, I can apply the same ideology in the first figure. If I remove the red circle, then I can slide this purple one outside this blue circle, and I can apply my R1 move, which is a removal of monogon, to make it trivial circle, which will be again a trivial doodle on two components. So now we will see a relationship between the Brownian doodle and twin. If I have a Brownian twin, and if I do the closure operation, what I get is Brownian doodle. The reason is, if you have for example, the figure I have here is just a Brownian twin. If I removing any strand is equivalent to removing a component in this diagram. So for a Brownian twin, removing a strand is same as removing a component in its closure. So thus, if I if I remove any component in this doodle, so it's same as I'm removing a strand in my twin. Since my twin is a Brownian twin, that become a trivial after removing that strand. Therefore, its closure is a trivial doodle. So this shows that this closure of Brownian twin is a Brownian doodle. But the converse is not true. There exists a Brownian doodle that cannot be obtained as a closure of Brownian twins. So before seeing an example for this, let's see a characterization which will characterize which Brownian doodle comes from the Brownian twin, for which we need the following lemma. If I have a twin and whose closure is a trivial doodle, then this twin is actually trivial twin. So the proof of this based on the fact that every doodle diagram has a minimal diagram representative, which is proved by the Cohen in his early paper called Doodle Groups. So every doodle has a unique minimal representative using which we can prove this following result. We also use some algebraic property of twin group to conclude this result. Having this lemma, we prove the following theorem that n component Brownian doodle on 2 sphere is a closure of Brownian twin if and only if its twin index is m, which is equal to the number of component integers. One side of proof is obvious. I will prove the other side. If D is a Brownian doodle on n component, and if its twin index is m, which means I can find a twin on m strand whose closure is this doodle D. And as we already noticed, removing any strand from W corresponds to removing a component of D. Okay. So what I need to show is now I need to show that this W is a Brownian twin. So let Wi be a twin obtained from W by removing the ith strand. So I need to show that this Wi is a trivial twin. Its closure is a trivial doodle for each I because my D is a Brownian doodle. Now I will use my previous lemma, which concludes that this Wi is a trivial twin for each I, which concludes that this is a Brownian twin. So having this lemma, the proof is now obvious that we proved that n component Brownian doodle on 2 sphere is a closure of Brownian twin if and only if its twin index is m. Now going back to the example I have before, the figure I have on the right hand side, on the left hand side is just a Brownian doodle, which means if I remove any of this component, I will get the trivial doodle. This can be seen as a closure of a twin on 4 strands. This figure illustrates that homotopy. How can I see this as a homotopy 4 strand? To say it's not a closure of a Brownian twin, I need to show that its twin index is not equal to 3, which is a number of component, and which follows because every 3 strand, when I do the closure operation, it will have a minimum representative. Its minimum representative will always have a multiple of 6 crossings, but the twin I have, the doodle I have as a crossing number 11. So which is not equal to which is not a multiple of 6, which concludes that this doodle cannot be written as a closure of a twin on 3 strands. So which is an example which is not a closure of Brownian twin. So in this direction, then we gave a enumeratable construction to construct all Brownian twin, for which we need a following definition. A twin on a is said to be k-decomposable if it becomes trivial after removing any k of its strands. For example, the 1 decomposable twins are Brownian twin. So the set of all k-decomposable twin forms a normal subgroups, and we denote the subgroup by dk, n. Then we gave an algorithm to construct dn minus 3, n in terms of pure twin and the coset representative of pure twin groups. And also we gave algorithm how to construct dkn minus 1, n from dk n. So inductively keep doing this algorithm, we can construct d1, n, which is a set of all twin group, Brownian twins. So thus this algorithm will illustrate that all Brownian twins can be enumeratively constructible. And we also studied the another generalization of Brownian twin, which is called Cohen twin, which is a twin on n strand is said to be Cohen if if we remove any of its strand, what we obtain is always same. That is what I want to say is a twin on n strand is said to be coherent if the twin obtained by removing any of its strands all are same. Or more explicitly, for each I, let's consider the map di. This is a map. It takes the n strand twin and it deletes its ith strand and it becomes now n-1 strands twin. This is not a group homomorphism, it's a set theory map. Now, a twin W is called a Cohen twin if image of the W under each of this map is same. That is D1 of W is same as D2 of W is same as Dn of W. If all of them become trivial, then that such a W is called Brownian twin. So that's why it's called a generalization of Brownian twin. So for example, I have 4 examples of Brownian twins. If I consider the second figure, if I remove this 4th strand, so what I obtain is the figure, the firstmost figure. Even if I remove any of the strand, what I will obtain is the firstmost figure. So all these 4 are example of Cohen twins. So then we gave a characterization of all Cohen twin. So this we prove the following theorem: the system of equation has a solution for W if and only if U satisfies this following condition, which means this W is a Cohen twin. Its image under each of this map is same. If W is a Cohen twin, if and only if this U is a Cohen twin on n-1 strands. The proof of this theorem is basically to explore the what is called phase map and co-phase map, which is called bi-delta structure on twin groups or pure twin groups. Using the bi-delta structure, we construct some map which will help in proving this theorem. So this is the paper I was speaking about. So Brownian planar braids on simplicial group. Thank you. I'm stopping here.
Thank you, Pravin. Any questions? Okay, let me ask one question. So you talked about some algorithm, right?
Yeah.
From k Brownian to 1 Brownian, that algorithm. Can you please elaborate a little bit what exactly, how you
yeah. See, let me fix that.
Yeah, this one.
My group is finitely generated, therefore it's anyway Tn itself a countable. So it's not very great result that I'm giving some enumerable algorithm. Every countable set can be constructed. Here we are giving one explicit algorithm. So first what we are doing is we are understanding the structure of Dn-3, n. Everything set theoretically, nothing group theoretically. That in other words, we are defining a set theoretic map from a pure twin to set of all Brownian twin, which form a retract map. That is, if I start with any twin, I will give we are given a construction which gives you a Brownian twin. If I start with Brownian twin, I will get back the same element. So we have just defined a retract map from the pure twin group to a Brownian twin groups.
What do you mean by retract map?
Yeah.
What do you mean by retract map? From
by retract map is a surjective. So let's say G and H is a subgroup of G. Okay. We say a map is retract from G to H if it is surjective, and when I restrict onto the subgroup H, it's identity map.
I see.
It's not a standard term in group theory, but it's a standard term in topology. So,
but the same idea, right?
Yeah. Then mimicking that idea, we can construct dk-1, n from dkn. And now doing this step one by one, d1, n is what my Brownian twin.
Right. Nice. Thank you. Any other questions? If not, let us thank the speaker.
Yeah, thank you. Thank you for giving me this opportunity.
Thank you, Pravin.